Hi everyone, I'm Yin Lin from the University of Michigan. I'm very happy to present our work on identifying insufficient coverage of databases with multiple relations. In today's data-driven world, automated decision systems are widely adopted in applications like healthcare, policing, resource allocation, criminal justice, and so on. In an ADS, first, data is collected, and then machine learning models train the decision-making system based on the collected datasets and generate the final decision. In spite of the wide adoption of ADS, they are seldom truly neutral and fair. Numerous examples show that minority groups are exposed to a higher risk of unfairness. The source of these biases is because data scientists have limited control over the data collection process and embed biases when collecting the data, and also because the data itself reflects existing inequity and prejudice in the real world. Based on the biased data, unintentional discrimination will appear in the decision-making process. It is important for data users to understand the representativeness and diversity of decision support datasets. Therefore, it is important to check the coverage in the early stage of data pipeline as a necessary data preprocessing step. In practice, data is commonly stored in databases or even data warehouses. Our coverage definition is based on the equal joint result of multiple tables. We define data pattern as a value assignment for a set of attributes of interest. In the data pattern, an attribute can either be bound to a deterministic value or be an unbound attribute, which means we don't care about its value assignment. For example, the pattern X production company means we don't care about the value assignment for the kind attribute, but the company type should be production companies. The coverage of a categorical group is the count result of a data pattern. We call a data pattern uncovered when the count result over its predicate restriction is lower than a given threshold. We want to determine whether there are enough records for each categorical group. We want to be alerted if, for example, in the movie recommendation datasets, all action movies are from big American studios, or all docudramas are from independent producers in recent years. In most situations, larger uncovered regions are more harmful than smaller ones. Therefore, our task is to find out all maximal uncovered patterns. We call them MUPs for short. We construct the pattern graph according to the dominant relationship of data patterns. We focus on the root of uncovered pattern trees to avoid outputting a long list of all nodes in the entire lattice space of pattern graph. The difficulty of MUP identification task comes for two main reasons. First, the queries to get the pattern coverage involve complex table joins and predicate restrictions from different tables. It would be hard for data users to write all these queries by themselves. Second, although the time overhead to execute one conjunctive count query won't be so long, it is intolerable given a combinatorial set of possible value combinations to explore. Efficient count optimization method and pattern graph traversal algorithm will be needed to address these challenges. Our proposed method contains three major components. We first build index structures to speed up the count query execution. For pattern graph coverage assessment, we aim to check whether the given data pattern is covered or not. The most time-consuming operation for the conjunctive count query is the join operation. Therefore, we base our index method on the join index technique to avoid actual join of tables. Although the join index materializes joint result in forms of row identifiers, we still need to access the original table to check where clause predicates. Therefore, we further propose a one-hot inverted index structure. It avoids accessing the original table and make the checking of predicate results to be completed in constant time complexity. The one-hot inverted index structure enables us to do an operation to combine filter results in the same table. However, we still need to refer to the join index when combining predicates from different tables. For the most commonly seen many-to-one joins, we propose to extend the bit arrays to construct universal inverted index structures. This final step makes the count operation to determine the pattern coverage a pure bitwise operation. We now look into the pattern graph traversal algorithms to reduce the number of count operations. We note that once we found an uncovered pattern, all its children are uncovered. Similarly, once we found a covered pattern, all its parents are covered. We apply this rule to prune the MOP searching process. To enumerate all data patterns, widely adopted lattice-based traversal algorithms include BFS-based, either going top-down or bottom-up, and DFS-based method. However, these methods treat all nodes the same and cannot make use of the pruning efficiency of different nodes. Our method assigns a higher priority to nodes that are connected to more neighbors in order to approach higher pruning efficiency. We also assign different weights for parent nodes and children nodes to balance the tendency of going deeper or exploring the same layer. We also design approximate coverage analysis method. Since for MOP identification, we don't need exact count results, so we consider using samplers to construct much smaller samples in one pass of the data, so our algorithm can work with much smaller data size. Since for MOP identification, we don't need exact count results, so we consider using samplers to construct much smaller samples in one pass of the data, so our algorithm can work with much smaller data size. You can check out more technical details in the paper. Now we discuss the experiment settings and results. The experiments using 3 real-world multiple table data sets. The data resides in PostgreSQL database systems. To determine the pattern coverage, we use conjunctive count query and group by query as baseline queries. We compare our method with 3 single table baseline algorithms. For the exact coverage analysis, we compare the execution time for MOP identification under varying coverage thresholds. It is shown that baseline method failed in some cases because of the enormous memory consumption to store the counts for bottom layer patterns, and the long execution time for numerous conjunctive count queries. Our method outperformed all baseline methods by efficiently accelerate pattern coverage assessment and reduce the number of patterns explored. For pattern coverage analysis, our index-based method outperforms other DBMS query optimization methods like materialized views and the column store systems under varying data size and query selectivity. For the priority-based searching algorithm, we examine the number of count operations needed by different algorithms. The priority-based algorithm reduced the times of counts and also made it close to the actual number of MOPs. This means we successfully approached the highest pruning efficiency. We also show the accuracy and efficiency of approximate coverage analysis method. To sum up, we studied the coverage in the training set used for machine learning decision-making systems. Given the large set of value assignment to explore, we first proposed an indexing schema to speed up the count operation. And then we designed a priority-based search algorithm to reduce the number of count operations. We proposed an approximate coverage analysis method to reduce the time overhead. That's all. Thanks for listening, and I'm happy to take questions.